Section 3.2, addition and subtraction of whole numbers. We worked through a lot of this section last time. In fact, we worked through everything that had to do with addition, I believe. And I believe we're at the point where we're about to talk about subtraction. Does that sound right to you guys? Awesome. All right, so let's take a look at how we're going to define subtraction. Subtraction of whole numbers. For any whole numbers A and B, where A is bigger or equal to B, A minus B is the unique whole number C such that B plus C equals A. This definition is exactly how students think about subtraction when they first are working with it for the first time. Usually, by the time they've hit subtraction, they've memorized some addition subtables for their addition facts, right? They have worked through some sort of timed test, or they're doing tests on computers that they're getting really quick at knowing that 5 plus 4 is equal to 9 and 2 plus 3 is equal to 5 and so forth. You with me? And so then we want to get them equipped to do the same thing with subtraction. And the first thing that we usually do is something like this. We want to talk about what 9 minus 5 is. And of course we want them to give the answer 4, right? But the way in which we do it is we say something like this. We say 5 plus what equals 9. We ask them the same question in terms of addition. And that's what this definition is saying. That 5 or 9 minus 5, for example, is the same thing as taking that 5 and figuring out what do I need to add to it to get my 9 back. It's the missing part. Okay? There are actually 4, I think it is. Yeah, 4 different models that we're going to do for addition and subtraction. We have exactly 8 students. I'm glad it's even. So everybody is near enough to somebody. You're going to be paired with them quite quickly in a temporary group for something, okay? So just kind of where you guys are. Jasmine, Rose, you'll be back with Lauren. Okay, and you girls in the front. Okay, everybody's got a partner. All right, so I'll tell you what to do when we get to that point. Let me talk to you first about the 4 models for subtraction. The first one is the takeaway model. This is the model that people tend to think about when they say subtraction. If you ask a young child what is subtraction, they will often say it's taking something away. You have something, you're taking something away. So for example, Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? And just like last time, I'm going to show you some of these, of course. In fact, I'm going to show all of them to you in terms of a concrete model or a picture. So we're going to have 24 rocks. Okay, so you guys need to draw 24 rocks too, all right? There are my 24 rocks. They even sort of look irregular, don't they? Kind of funny edges and stuff. 24 rocks. And Eli sneaks in and he takes 5 of them away. So we're going to remove 5 of the rocks from the picture. He has stolen them, and Abby's going to be unhappy. And of course, the question is how many remain. We could physically count this up again, and we would find out that the answer is 19 rocks. Okay, we physically removed something. When we talk about these models, models are not the picture. The models are the verbal description of what's happening. In this description, somebody is taking something away from what they already have. You have something and you're removing part of it. Now, that's different than the next example. The next example is called missing addends. Lilise needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more does Lilise need? She doesn't have them yet, right? In the last example, actually, Abby had 24 rocks. She's missing something to get to the value she needs. That's different. You probably don't even feel like it's different because you've seen these kinds of questions so long. But for a child, this feels very different than the last question. And if you're working with a kid through word problems about subtraction and you can identify that every problem they miss is this kind, that gives you a lot better information about how to help that kid, doesn't it? It really does. So that's why we're looking at this. Okay, so what do we have? Well, we have leaves. So we're going to draw the leaves that she has. How many leaves does she have? What did it say? 8? Okay, there are 8 leaves that she has. Those don't look nearly as close to leaves as my last example looked like rocks. And we want 10. So the visual imagery of what we do is that we draw in sort of like dotted images of what's missing. So let me show you. Ah, that's not what I wanted. Let me try again. That'll work. All right, they're not there. That's why it's hollow. Okay, they're the missing ones. But now my image actually, if I count those 2, has 10 in it. There are now 10 here, right? And then the answer is the missing pieces. She needs 2 leaves. You can also do this, and it feels a lot like the definition of subtraction, where you're saying you have 8, how many do you need to add to it to get to 10? Right? What's the missing piece? What has to go in here to make this actually work? And of course the answer is 2. So our solution is 2 leaves. So it doesn't have to be drawn in picture form. It can be, but you can also do it in sort of like an equation form of the missing piece.
Would you say that when trying to decide what kind of equation or what kind of model it's going to be, would you say that how many more would represent good for missing addends? Like that would be key to know?
Probably. You'll see the word missing a lot, or how many more does she need, or what is she missing? Those kinds of phrases you'll see used a lot. Yep, I would agree. All right. Comparison model. Madeline and Monique play basketball. Madeline scored 12 points and Monique scored 8. How many more points did Madeline score than Monique? Here, we're not taking anything away, and we're not missing anything either, are we? We're comparing 2 things. It's still a subtraction problem. So, in terms of drawing a picture, I'm going to draw this one with just hash marks, you know, like you would tally points up. So we have Madeline, Monique. The first one, let's see, Madeline scored 12 points. So there's Madeline's score. And then Monique scored 8 points. And you don't have to hash, cross out the 5s if you don't want to. It makes it a little bit less convenient actually to do so, to do the comparison. But the question is, how many is missing? What in here is not there compared to the first one? It's the missing piece. It's the difference. The difference by comparison. And of course the answer is what? 4. There are 4 points missing. It's not takeaway. It's not missing addends. The last one is something we've seen before. We had a number line model for addition. The whole key about number lines is that whatever the object is, it can be broken into pieces and makes sense. Okay? So you don't have number lines models of people. You have number line models of things that have the ability to be divided. This is an example. It's miles. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls to ask him where he is. He states that he is coming home and has driven 8 miles so far. How far is Akeem from home? It's a number line model. So we're going to draw that. Here's home, and here's the mall. It's just a bigger home because I can't draw. So that's what we're going to do. All right, so we start at 0. And we know that he's 15 miles when he's actually at the mall, right? And he tells his mom he has driven 8 miles so far. So wherever he is, he's 8 miles back this way, correct? So the question is, how far does that put him, either like that or like this, to get home? right? And the reason it's a number line model is because it's miles. I mean, that's really it. It's a number line model because it's miles. So, what would the answer be? He would be 7 miles from home. And now if you actually did this, of course, on a number line grid, the answer would already be right here, wouldn't it? Like you would have already had them marked out. 1, 2, 3, 4, 5, 6. They're definitely not to scale because that's 7. 8, 9, 10, 11, 12, 13, 14, and 15. Also not to scale. Yours would be much better, I'm sure. But it would actually be at 7 if we actually drew the number line out in advance of doing this, right? So a child would actually see, well, how far is he from home? Well, he's 7 because that's the number that I'm on. Okay, so here is your assignment for the next 4 minutes. You get 1 minute per problem. You and your partner next to you are going to create 4 examples. I don't need an answer. I don't need a drawing. You're creating 4 word problems. That's what you're creating. A word problem for the takeaway model, a word problem for the missing addends model, a word problem for comparison, and a word problem for number line. All right? They need to be applicable and interesting to young children. So for example, this last one that I gave, not so applicable. 5-year-old does not care about driving. They don't drive to the mall. Are you with me? So if you're doing a number line model, it needs to be something that makes sense of what they would actually make value of in that case. Make sense? All right, give it a try. All right, we have 4 groups and we have 4 examples, right? So every group is going to get to give me 1 example. Somebody give me your example for what your takeaway one is.
Tina had 5 cookies. She ate 2. How many did she have left?
All right, she ate 5 cookies. She had 5 cookies, she ate 2. How many does she have left? That's a great takeaway model. Somebody else for their missing addends, what'd you do?
Laura needs 8 different colored crowns to color a picture. She has 5 different colored crowns. How many does she need to borrow from a friend?
Excellent. So she needs 8. She only has 5, so we're going to borrow some from a friend. Fantastic. All right, we got 2 groups left. Who's going to do comparison? All right, Lauren.
Lauren hits 3 home runs in 1 game, and Lizzie hits 1 home run in that same game. How many more home runs does Lauren hit than Lizzie?
Good. All right, so we're doing comparison of home runs. All right, ladies, you're the last one. Let's see what your number line model was.
Okay. We did Rachel ran 20 feet, and her teacher told her to come back. She ran 12 feet back. How many more feet does she have to run to make it back to her teacher?
Good. That'll work. All right, so we've got the feet comparison. All right, we have 1 more slide, and then we're done for the, well, I guess it's 2 more slides. 1 more page on your notes. We're done with these. The question asks us, which of the following properties hold for subtraction? And we talked about some of these last time when we were talking about these properties inside of the idea of addition. So closure, let me remind you again what closure means. Closure is the idea of having all of these kinds of numbers, this type of number right now is whole numbers, floating around in the room in here, and the door is closed. So if I were to take 2 whole numbers and I were to subtract them, will I automatically get another whole number? Not always, right? So somebody give me an example why this does not hold. All right, 2 minus 5 is 3, and 3 is not an element of the whole numbers. Oh, I'm sorry, thank you. Negative 3 is not an element of the whole numbers. You've seen those symbols now, right? Not an element of whole numbers. It's not whole. How about commutative? If I subtract 2 numbers, and then I switch the order of the subtraction, is that going to work? No, it's not. Can somebody give me an example?
-3 and 3 minus 2.
All right, 3 minus 2 would be just fine, right? This is equal to 1. But 2 minus 3 in the reverse order gives me -1. And these are not equal. And they should be if it were commutative. Associative. You might actually need to check on this one because you might not be able to do this one off the top of your head because you're going to have to pick 3 numbers. So let's just pick 3 numbers. Somebody pick me 3 numbers and let's make them in order from biggest to smallest. So somebody pick me a big, I don't want a big number. Don't be ridiculous. Thank you. 8 minus 4 minus 1. And then I'm going to do 8 minus 4 minus 1. And we're going to check it out. So if I do 8 minus 4, I get 4. And 4 minus 1 is 3. Okay, so that's 3. On the second line, if I do 4 minus 1, I get 3. And then I do 8 minus 3, I get 5. So I didn't have anything negative come up, and the reason I didn't is because I asked you guys to pick them in order from biggest to smallest so that it wouldn't actually come up. But this isn't equal. And really, almost any numbers you pick won't work with this either. So this one does not work either. How about the identity property? Do you remember the identity property, Seb? Right. The additive identity is the number 0 because if we add 0 to anything, we get back the same number. So let's try this with the number 0. So if I did 0 away from 5, I get 5. And it feels like maybe that would work. But look back at the additive identity property. It didn't just say 5 plus 0. It also said, yeah, it said we needed to be able to do it in both directions, which would mean I'd have to be able to do this as well. And what happens when I try to do 0 minus 5? That's negative 5. This does not equal the same value that I got before, right? It's not the same value I started with. So there is not an identity property either. It almost feels like we should be able to say something like there's a half identity or something, because it works halfway, right? One direction. But because it doesn't work both directions, it is not considered to be an identity element for the whole number system. Okay? Everybody good? Awesome.